Hello student, very good morning to all of you. How are you? I hope you all are happy, healthy and fine at home. Do you remember what were we discussing yesterday? I think we were discussing about beer vinegar rearrangement reaction. So what does it mean? What are the starting material and what are the products? How what kind of the stereochemistry involved in it and how to remember. So that type of the thing we were discussed yesterday, and today what we are going to discuss, today we are going to discuss the remaining part of that beer vinegar rearrangement reaction, that is a beer vinegar rearrangement reaction we are talking. So general reaction we have seen, and what are the generally the per acids are employed for this reaction, and we are getting the formation of the product. Generally beer vinegar oxidation reaction means what? A reaction in which the ketone is converted into ester with the help of per acid. So that kind of the reaction are known as beer vinegar rearrangement reaction. And as we know that rearrangement reaction means what? A reaction in which the carbon skeleton or the functional group or both are modified is known as rearrangement reaction. Let us discuss. Let us start with the beer vinegar oxidation reaction, general reaction. Yesterday we have seen, suppose you have a starting compound is like this, R C double bond O R dash, that will be treated with the per acid, and generally per acid is used as a performic acid or per acetic acid or per benzoic acid or metachloro per benzoic acid. These are the common reagent used for beer vinegar oxidation reaction, right? And now when only the trick you should remember, where this ketone, this is the general formula of ketone, as we know that, right? This is the general formula of ketone. The organic compound having general formula R C double bond O R dash is known as a ketone. And now when it is treated, or when it is when ketone is allowed to react with per acid, it forms this one R C double bond O R dash. This is an ester. Understood this one? So what we did over here, this ketone is converted into as a ester with the help of per acid. This reaction is known as beer vinegar rearrangement reaction, or it is referred as beer vinegar oxidation. Oxidation means addition of oxygen atom. Look at here, ketone having as a one carbonyl group, and here we added one oxygen atom. We inserted one oxygen atom in between these two carbon atom, and we got as an ester. This is the general reaction of beer vinegar oxidation reaction, and the mechanism of that we learned yesterday. But let us see here how the mechanisms are taking place once again over here with the help of some example. Let us look at here. Cyclic ketone gives lactone. Do you remember the lactone, structure of lactone? As I already told you that lactone is nothing but as a ester, but a cyclic ester is known as a lactone, and cyclic amides are known as a lactone. And general formula of amide, everybody knows that R C double bond O NH2 is known as a amide. When that open chain, when that amides are in a open chain, then we can call it as a amide. But when it is present in a cyclic form, then the common name of that organic species are called as a lactone. Remember, and the open chain of esters are generally known as a aliphatic or maybe as aromatic. They are the ester open chain. But when that esters are involved in a cyclic form, that structures are known as a lactone. Please remember these words, lactone. So let us see here the example of, for example, cyclic ketone gives lactone. Cyclic ketone gives lactone. One example we are going to see over here. Example number, these are the example we are talking. Example number 1, cyclic ketones gives lactone. Cyclic ketone gives lactone. So this lactone. So cyclic ketone gives the lactone. How the cyclic ketone gives the lactone? Let us see here. Simplest ketone. Here suppose you have this one, C double bond O. This is a cyclic pentanone. This is known as a cyclic pentanone. Pent indicate as a 5 carbon atom in the cycle, and therefore it is known as a cyclic pentanone. When it is treated with the per acid, for example, suppose let us see here R C double bond OH. This is a per acid. This is a beer vinegar rearrangement reaction, BVR. So we can call it, and so here we are going to get the product is this one, and this is known as a lactone. The cyclic ester, this is a ester are involved in a cyclic form, and therefore this is known as a lactone. Here this point clearly indicate that cyclic ketone gives a lactone, and this is a lactone. Now see here how we get that lactone. Let us look at as a mechanism, and as we know that mechanism definition of the mechanism we have heard, we have said many times, number of time we have seen that the definition of that mechanism, a detailed study of sequence of steps which are involved in the conversion of reactant into product is known as mechanism. And the organic chemistry mechanism is the language of organic chemistry, and so let us see over here how this lactone is formed. Here let us see, here starting compound we have a cyclic pentone or cyclopentanone, cyclohexanone, cyclopentanone, cyclobutanone, cyclopropanone. So that type of the general names are given for the, suppose we have this one, this is called as a cyclopropanone. Suppose you have a 4-member ring, C double bond O, we can call it as a cyclobutanone. Suppose you have a this one, then we can call it, this one is a cyclopentanone. And suppose you have a 6-member ring, so this is known as a cyclohexanone. So these are the common names of this type of the cyclic ketones. So this is a example of cyclopentanone when it is treated with the per acid. Let us see here, I am going to use over here per acid, that is per acetic acid, CH3 C double bond O and H over there, right? And now what is going to happen here, the lone pair which is present on that oxygen atom is going to attack on this carbonyl group, and you are going to get the product is like this. Here O minus, and here we can write O, then double bond O, here CH3 I am writing, and here this CH positive charge over there, and that positive charge normally here there is a loss of proton over there. After losing the proton, what type of the species you are going to get over here? Here O minus, then O, I am writing O, then C double bond O, CS3, peracetic acid, right? Now what is going to happen here? The rearrangement reaction occur here. Rearrangement means what? The atoms are perfectly rearranged, carbon skeleton are nicely rearranged, and we will get here C double bond. There is a carbonyl group form over there. Now this double bond is shifted from this after the bond is breaking from here. Look at here, carbon never form as a 5 bond, never show the 5 bond, because carbon is a tetravalency as we know that, and that's why when this negative charge forming as a double bond between this oxygen atom and this carbon atom, ultimately the driving force behind breaking of this bond, so it break like this, and it is this bond is going to attack on that oxygen atom, because here this oxygen atom is electron deficient in nature, and this bond, the oxygen bond is a very weak bond, it cleaved very easily, and what do you get over here? You are going to get over here this one C double bond O. This oxygen atom now comes into the ring, and you are going to get this 5 member, generally 5 member ring becomes as a this type of the 6 member ring, and this is nothing but as a lactone. Understood this? This is one of the example how we can apply the Baeyer-Villiger rearrangement reaction here. Now let us move on to the next example. Now the example number 2nd, which we are going to see over here. Let's see what will be the next example which we are going to discuss over here. The example we are talking about the Baeyer-Villiger rearrangement reaction. Second example, labeled oxygen in ketone is retained in the ester. Labeled oxygen. Example number 2nd, labeled oxygen in ketone. Labeled oxygen in ketone is retained in the ester. And as we know that labeled oxygen atom, as we know that this is one of the experiment, and this experiment proves that whether the oxygen atom which is present in the ketone is found in the when there is a formation of the product, or it is lost. Whether that carbonyl oxygen atom, when it is labeled, then we come to know that this carbonyl, whether it is as it is from which is present in the ketone, is retained or not. For that purpose, the labeled experiment is carried out or done to prove the presence of carbonyl group is seen in the formation of the product, and other because we are using as a per acid, so there is a possibility of that carbonyl group also present in the per acid. Does that carbonyl group the coming from ketone or from per acid? That's the point of discussion. So for labeling, what the purpose of labeling that oxygen atom, here the scientists, this Baeyer-Villiger scientists, trying to prove the carbonyl group which is coming from the ketone, not from the per acid. So that's why it is known as a labeled oxygen. Oxygen, it is generally labeled, means that oxygen atom are used as a higher isotopes. And isotope, we know that isotope means what? Atomic numbers are same but their mass numbers are different, and therefore there are the different isotope of oxygen. General or the normal isotope of normal oxygen having as a mass number is a 16, isotope maybe as a 17, generally as a 18, and like this. So labeled oxygen, generally you remember it is increased by 2 units, so that oxygen atom, and therefore we are going to see over here the labeled oxygen. Here we are going to use as a symmetrical aromatic ketone, as we know that C double bond O. Here this is the aromatic ketone. I have taken labeling as a O oxygen atom. Normally the 16 we are not mentioning their atomic mass, but when the labeling experiments are done, then we have to mention the atomic weight of that oxygen atom is 18, and the name of this compound is a benzo, what we can call it, benzophenone, right? This is the benzophenone, labeled benzophenone. So benzophenone, on both the side phenyl group, the phenyl group are identical, it is a symmetrical ketone, and now when it is treated with metachloroperbenzoic acid, let us see. This is one of the as we know that the structure of that metachloroperbenzoic acid is like this. Suppose we have H, then O, then C double bond O, we can write this one, metachloroperbenzoic acid. This is the structure of metachloroperbenzoic acid. What you are going to get, the product is going to form over here, this one. Let us see here, C double bond O, then O, then you are going to get this type of the compound. So simple, only ester group is, only oxygen atom is insert. There are these symmetrical, so you can insert oxygen atom either this side or this side. It doesn't make any difference because both the phenyl group are identical, and that's why we will get the product like this. Now why we are getting as a that type of the product, let's see the mechanism once again over here. Mechanism, as we know that this phenyl, instead of this big molecule, in short, to save the time or to show the clarity, I am writing here, instead of that phenyl structure, I am writing pH only, C double bond O, then here also as a pH, and now plus HO, then O, then this one that we have to write here, metachloroperbenzoic acid. Sorry, here is a one more C double bond O carbonyl group is there. So it is going to attack over there as it is, as usual. What do you get here? pH, then C, O minus, then O, one hydrogen atom here, O, then C double bond O, then this phenyl group, as we know that at meta position chlorine group I am writing here like this, and then pH. I can attach that pH either this side or this side, doesn't matter over there. Now the here positive charge, why I am putting as a positive charge on this oxygen atom? Because look at normal bond of that oxygen atom are 2, now here is a 3, and that's why positive. Whenever positive charge coming on that oxygen atom, it is very unstable. Now that positive charge get neutralized by losing the proton, and you may get here pH, then CO minus, then here O, then another C double bond O, this ring, and Cl group is there, and this one is a pH. Now the rearrangement reaction generally occurs over there, this negative charge forming as a double bond over there. Now this group is a migrating group, so it migrate from here to here, and there is a that metachlorobenzoic acid is generated over there, and now you will get over here pH, C double bond O, and this pH. This is an phenyl benzoate or benzene benzoate you are going to get over there. So this is the experiment, and here look at here 18 labeled oxygen atom. I am not mentioning here, so remember 18 over here again as 18, and that 18 is that 18 oxygen atom, labeled oxygen atom is found in product, and therefore it is inferred that the carbonyl carbon which is retained in the product when ketone is converted into the ester. So that is the second example which we have learned here. Now let us discuss about the example number 3. What will be the example number 3 that we will going to discuss shortly. Before that, let me clean the board, and now let's have look at the third example, that is migration of phenyl group over cyclopropyl group. Migration, third example, migration of phenyl group, migration of phenyl group or cyclopropyl group. That's the point of discussion. Let us see over here the example here. Which example we are going to see here? Let us see here this one, then C double bond O, then here is a phenyl group. And now let us see, when we are using the per acid may be as a trifluoro acid CF3, then C double bond OH. This we know that we are using different per acids, but the main reason here, main point you should remember here, yesterday we have seen the migratory aptitude, or the which group is migrate faster than which group. Generally tertiary alkyl group migrate faster than secondary, than phenyl, than benzyl, and then primary, then methyl, like this. So that are the sequence of migratory aptitude, means the how that group are migrate, why one which is more migrating over the another, that thing we already learned over there. Now here look at this is an unsymmetrical ketone. Now the oxygen atom is going to insert, and resulting compound is going to form as an ester, and therefore what, either you think over here, whether the oxygen atom which you are going to insert either on phenyl group or on cyclopropyl group, or the one sentence is clearly written on the board. What is that? Migration of phenyl group over the cyclopropyl group means this phenyl group is migrate faster than the cyclopropyl group, and therefore without thinking you can insert, you will get, while predict the product, you can predict the product very easily. Just write the structure as it is, C double bond O, then now insert oxygen atom, and here you will get this one, that is a phenyl group. Only this is the product you are going to get. So simple. And mechanism, as we know that mechanisms are again so simple. Let us look at again as a mechanism, so that you have to practice again and again for organic compound. And then, as we know, that one proverb is there, practice makes man perfect. So you try to write these organic compounds again and again. You will become familiar with this organic compound, and so that you can predict any product whichever is given, but you must know the mechanism behind it. Why I am predicting this product? Because I know the mechanism behind it, and that's why I am predicting that one. So let's see over here. Let us see the mechanism once again over here. This one triphenyl, then C double bond O, then this, instead of that phenyl ring I am writing shortly PH, so that, and then this one HO, then O, C double bond O, CF3 I am writing like this. So this lone pair is going to attack on the carbonyl carbon, and you are going to get the product like this. This one, then CO minus, now here OH, then O, C double bond O, then CF3, this the CF3, and now here is a phenyl we are writing. Now I am putting as a positive charge on that oxygen atom, the reason you know behind it, right? And now there is a loss of that proton. After losing that proton, what do you get? The intermediate which you are going to get over here. This one oxygen atom, another oxygen atom, C double bond O, CF3, and now this one is a pH. Now the actual rearrangement reaction occurs over there. This negative charge coming down, forming as a double bond. When double bond form, it pushing that phenyl group from here to here, and this the trifluoroacetic acid compound we are getting. But we are not worry, or you do not need to worry, you need not worry about that side product. Just focus on the main product which we are getting over here. This one C double bond O, oxygen, because this oxygen atom goes in there, and then there is a pH. So this is the product which we got over here. So these are the example. Now the example number 4 which we are going to consider over here. What will be the example, and more information we will get about this Baeyer vinegar oxidation reaction. So let's see what will be the fourth point we are going to discuss. Let's have consider one more example over there. Example number 4, which is given in the book. Migration of methoxyphenyl group or phenyl group. What is given here? Migration of. It is having similarity with the I think example number 3rd one is the same. Migration of methoxyphenyl group or phenyl group, right? So this is the example what they are trying, what I am trying to explain over there. Migration of methoxyphenyl group or phenyl group. You should remember here the migratory aptitude. Here methoxy, as we know that it is an electron donating moiety attached to that benzene ring, and phenyl is a plain benzene ring. So let us see the structure over here. How we can draw the structure? This is suppose as a phenyl group, right? C double bond O, and then we can write as a this one here OCH3. This is the name of this compound, is a paramethoxy benzophenone. You can call it as a paramethoxy benzophenone. Now when it is treated with suppose as a H C double bond OH, the name of this compound is a performic acid. Performic acid. This is the name of that per acid and what you are going to get? The product. Now remember here, this is an unsymmetrical ketone. On one side there is a phenyl group and other side containing as a one methoxy group. Methoxy group is a electron donating group. When electron donating group present over there, these migrate very easily, and therefore you are going to get the product is this one. Let us see here, C double bond O. Now the oxygen is going to insert over here O, then this one, that methoxy group OCS3, right? This is the product which we got over there. Now let's see the mechanism once again over here. If you know the mechanism, you can very clearly understood the organic chemistry. Let's see here. For clarity or to save the time, I am writing that phenyl group in short, pH, C double bond O. Then this phenyl group you should mention as it is because it is connecting to that paramethoxy, and now there is a HO, C double bond O, then hydrogen atom. The lone pair which is present on that oxygen atom is attacking on that carbonyl carbon, and you are going to get pH C O minus, then this methoxy group which is as it is OCS3, here O, then H, O, C double bond O, H as it is. And now look at again, this oxygen atom has a positive charge. Why I am putting positive charge? You know the reason behind it, right? Now this is going to, after losing that hydrogen atom, so that species become as a stable pH, then CO minus, then O here, O, then O, C double bond O, and hydrogen atom over there, and here you can write this species as it is OCS3. Now the actual rearrangement reaction takes place over here. Rearrangement, this negative charge coming down, forming as a double bond with that oxygen atom, and this, even though it is a bigger group, but it is a migrate faster on this oxygen atom, and then we are going to get the product is this one pH, then C double bond O, then O, then here is a this one OCS3. This is the product which we got over here. So in this way, the clear migration of methoxyphenyl group over the phenyl group. So this is the example of that. Now the use of above oxidation in various field in industries like this. Above oxidation reaction can be extended for the preparation of acids from esters, that is ketone can be converted to acid via ester, benzaldehyde to benzoic acid, and phenol Duckine reaction, and some enzymes are also useful in converting ketone to ester or lactone. That is a very good because they have the selectivity or the stereo selective. You might be heard about stereo selective, stereo specific. Stereo selective means what? Whenever we are adding as a reagent, there always we are getting as a two product. For example, in case of an Selective reaction, generally if there are the two beta hydrogen atoms are there, then we are getting as a two product, and among these one is a major and another one is a minor. So that type of the reaction are known as a stereo selective reaction. And stereo specific reaction means what? Once you are going to get only and only one product, so that type of the reaction is known as a stereo specific reaction, and that depend upon the nature of the reagent and the nature of the starting material or the nature of the substrate which we are using here. And for example, let us see here which enzyme In beer vinegar oxidation reaction, it is a improved what we can call it as a concept for cyclohexanone to lactone we are going to get, but here for example by using as a enzyme, some enzyme are also useful in converting ketone to ester or lactone. For example, cyclohexanone oxygenase, that is the enzyme used over there. For example, here suppose you have this cyclohexanone and that will be treated with the enzyme like as a cyclohexanone oxygenase, that type of the enzyme. Generally the enzyme is NADPH and O2. This type of the what we can call it as a enzyme is employed here. And they got the lactone like this. Now it's a 6-member ring and you are going to get as a 7-member ring like this. So this is the lactone which we got over here. I think we have learned number of example based on that beer vinegar oxidation reaction. Let me quickly revise here again what are the important points you should remember as per as beer vinegar oxidation reaction is concerned or beer vinegar rearrangement reaction. Number 1, you should remember here is a starting material always is used as a ketone and that ketone is converted into an ester or sometime in acid, but don't think about that. But the reagent used here is a per acid, generally performic acid, per acetic acid or per benzoic acid or metachloro per benzoic acid, which is the commercially available reagent. So most of the time it is used in the it is available in the laboratory, so we can use it very easily and we can carry out the reaction at a ordinary reaction condition. Ordinary reaction condition means what? The temperature, whatever room temperature generally, then what we can call it as a it does not require as a heat, so you can store at a room temperature. So that are the some of the condition you can use over there. And one more thing, remember, while formation of the ester, if cyclic ketones are there, it is converted into as a lactone, means oxygen atom is inserted over there and we are getting as a formation of the lactone. And if suppose as unsymmetrical acids are, for example, let me give one example over here. Suppose you have this one C double bond and one methyl group is here. For sake of convenience, I am decreasing here, shortening the length. 5-member ring. What I did, I put one side, there is a methyl group and that ketone becomes as unsymmetrical. When I am going to use as a per acid over here, per acid, for example CS3, C double bond O and OH. This per acid, what type of the product I am going to get over here. So here question is that the oxygen you are going to insert on the right hand side or on the left hand side. Remember, from those side is a bulkiness. Here methyl group is there, so that you can get the product is like this. So this is the product which you are a 5-member ring is going to become as a 6-member ring, and this is the product lactone you are going to get. So this is the trick you should remember as per as a beer vinegar rearrangement reaction is concerned. I think tomorrow's lecture we will see the remaining rearrangement reaction. I think next reaction we are going to learn as a pinacolan rearrangement reaction. But here today we have seen the complete beer vinegar reaction. We have taken number of example. I hope you all are what we can understood this Baer vinegar oxidation reaction or Baer vinegar reaction means what. And I think with this, let us stop today here. Remaining we will see tomorrow. Thank you. Have a nice day.